Good afternoon. In this talk, we will tell you about our feasibility study on novel digital twins for monitoring compliance debt as part of the stream on data-driven manufacturing, regulation, and standards. I'm Rami Bahsoon, principal investigator on the project, and I'm joined by Carlos Gomez, a postdoc on the project, and Nanzang, a PhD contributing to the project. The presenting team have interest in software architecture of cyber-physical system, digital twins, and technical debt. Other team members include Professor Duke Pham, expert in autonomous manufacturing, Georgios Thidropoulos, expert in distributed simulation. Industrial collaborator is Uptime Institute, London. The project takes a broad view to compliance, where we view compliance as a responsibility to operate in agreement with established laws, regulation, standards, and specifications, and service level agreement. However, ensuring full compliance in digital manufacturing can be challenging and difficult to achieve, and you may need to ensure compliance across various layers, including cyber-physical infrastructure for resilience, compliance in the data layer for security, protection, and integrity, compliance for safety in process and control, and once you engineer intelligence following the principle of responsibility, transparency in design, as you keep a human in the loop. Given that manufacturing is essentially a cyber-physical system that operates under numerous operational uncertainties, this means that it can be difficult to fully comply in the presence of uncertainties encountered in operational environment. This entered the system into a debt. As the spectrum of compliance debt can be huge and can cross-cut processes, product, people, infrastructure, it's expected that smart manufacturing compliance engineers would take or enter into a debt somewhere when managing compliance. The debt can be accidental or intentional for time and cost saving. The project is the first to seek an understanding of the concept of compliance and compliance debt in smart remanufacturing, with cases from remanufacturing domain considering compliance that relates to processes, people, human, and when human machine work hand in hand in the production process. The feasibility study has resulted in reference architecture models for cognitive digital twins and novel adaptive technical debt models for compliance management in smart manufacturing. The goal is to provide smart manufacturing quality assurance engineers with tools that can assist in what-if analysis for compliance and likely debts to make compliance debt visible and transparent through digital twin analysis, and to rethink way to pay that debt through design, refinement, integration, policy change, and enforcement, or phasing out. The ambition is to promote interactive, predictive, or proactive intervention to reduce and mitigate the risk in compliance violation. Nan will provide an overview of cases and contributions that relates to digital twins, and Carlos will discuss results related to adaptive technical debt.
Okay, so there are different types of compliance sources. Here are some examples. So first, there could be industrial regulations like the Cyber Physical Information Sharing Act or GDPR, General Data Protection Regulation. Another type could be the standards, data security standards, like for the payment or the ISO series. Here we consider safety compliance as an example. The figure shows human-robot collaboration for safety compliance. The robot adjusts its operating speed depending on the distance between itself and a human operator. As shown in the first row, when the person is far away, the robot operates at full speed. But as the person walks closer, the robot will slow down to ensure safety compliance so that it will not harm the person. Based on this idea, we have further formulated a use case. The use case is about the trade-off between safety and efficiency in an assembly line or disassembly line. The workers may move and collaborate with different robots, and each robot here is implemented with compliance rules. And one example of rules is when a worker enters the safety range of the robot will slow down. However, reducing operating speed, as shown in the previous figures, could cause delay of task. There's a trade-off, therefore, between how much excessive safety we want to ensure and the efficiency of the task. And this figure shows exactly the use case. And the digital twin can help to evaluate different parameters of the rules in the simulation. And essentially, there are two parameters: the safety range and how much the robot should slow down. One of our contributions is the design and implementation of the digital twin for the human-robot collaboration use case. The figure here shows the generic architectural model of the digital twin. Here, the physical space at the bottom of the figure is abstracted as multiple agents interacting with the environment. And the middle layer, the digital twin maintains an equivalent simulation model through continuous sensing, update, and calibration, such that the model could make accurate predictions about the physical space. Then the decision maker at the top could extrapolate different what-if scenarios in the simulation in real time to gain insights for decisions that leads to the best outcome without affecting the real system. To map the generic architecture to compliance problems, here we consider the agents here in the use case are the robots, and the environment is the assembly line. We continuously monitor the status of compliance with a compliance model and use simulation in real time to evaluate what if different alternatives rules are encoded in the agents and which rules can improve compliance in the current context in real time. Then the rules lead to the best compliance will be applied back to the physical system.
So we are using the scenario of electrical vehicles battery remanufacturing, in which collaborative cobots can support humans during the disassembly operation, in which they can handle heavy and bulky objects, or they can automate repetitive tasks. And we are aware that cobots can speed up the productivity during the disassembly operation, as long as they comply with safety assurance standards, such as the ISO 10208, 1 and 2. In here, we have an aerial and lateral view of a cobot disassembly workstation for lithium-ion batteries, right? In which we can appreciate this shared workspace in which all this elastic model described by Nan a few slides ago takes place. But in general, adaptive compliance refers to the capability of a system to aim the satisfaction of multiple compliance sources in the presence of runtime variability. Smart remanufacturing can benefit from a digital twin equipped with depth-aware capabilities to reason about multiple sources of compliance, right? Such as law, regulation, standards, and so on. Sources that can partially overlap or even conflict with each other, such as the conflict between the safety standards and productivity requirements. Understand the compliance depth as the evaluation of the gap between the actual and the ideal compliance management decision, in such a way that any diversion from the hypothetical compliance optimality is considered as an indication of depth. This reasoning about compliance depth can help us to refine compliance policies before they are applied in the physical system. And we know that this depth, this compliance depth, can be learned, can be anticipated, can be analyzed in retrospective, because we already implemented it into another adaptive setting. We implemented the reinforcement learning agents that were able to learn technical depths in elasticity management. And similar to what we did there, now we are implementing a conceptual model for adaptive compliance, in which we have here the digital twin that represents the physical system that must comply with different compliance sources in the context of smart remanufacturing with some business goals. So the digital twin each time makes a decision under environmental uncertainty, it may introduce a compliance depth. And all this reasoning help us to raise the visibility of the trade-off between different compliance sources, about the value which can be analyzed in retrospective, in retrospective, proactively or reactive way, and even about the levels, the degrees of compliance with the different compliance sources. So now I am leaving Rami to end the talk.
I have to thank the Connected Everything Network coordinators and managers for the great opportunity for and funding for conducting fundamental and blue skies research. If you have any questions or you are interested in collaboration, please do not hesitate to contact us. And thank you.